Okay, so last video of the unit on quadratic sequences. So in the previous video, you um, you kind of learned what they were or how to tell if a sequence is quadratic, but here we'll learn really what they are and how to find closed form formulas for them. Uh, so here's an example. Y is the sequence 1, 2, 9, 22, 41, a quadratic sequence. Whoops. So why is it a quadratic sequence? Well, in the video you saw that if the second difference is constant, then it's quadratic. But what does that mean exactly? So just to recap, right? So if I look at the first difference or how much do I have to add by to get to from one term to the next term? Well, to get from 1 to 2, I add 1. I'll change the colors here maybe. To get from 2 to 9, I add 7. To get from 9 to 22, I add 13. And to get from 22 to 41, I add 19. Um, and so this is called the first difference. So if all these are the same, then it's in arithmetic or linear sequence, but they're not all the same. So it's not linear, uh, but it is quadratic because if we take the difference of the differences, um, then it is the second difference, the difference of the differences, is constant because we see here to get from 1 to 7, we add 6. To get from 7 to 13, we add 6. And to get from 13 to 19, we add 6. So you should say first differences, second differences. So if all second differences are the same, then the sequence is quadratic. So that's a good way to identify if a sequence is quadratic or not. Um, but what really is a quadratic sequence? And the hint is in the name. Um, it's a sequence of the form an, so the nth term of the sequence is a quadratic when n is thought of as the variable. So there will be three constants, a, b, and c. Um, I'm using capital letters because I didn't want the a coefficient to get confused with the a sub n, the nth term. So a sub n is of this form. So the nth term is always, it's given by a quadratic. So this is the closed form formula. Just like a linear sequence, an is linear in n. It is a linear formula. Um, so quadratic sequences, just like quadratic functions, grow much faster than linear functions. And this isn't, I mean, you're not necessarily taking calculus in the future, but it's important to kind of talk about rates of change, I think. So for linear sequences or for arithmetic sequences, the first difference is constant. That's the rate of change. The rate of change is, always 6 or always 3. Um, so constant rate of change, and if you graphed it, it would be a line, like with certain slope, and that slope is the rate of change. Um, And then for a quadratic sequence, right, the rate of change is not constant, but the rate of change of the rate of change is. And if you want to talk about a physical interpretation of that, well, if you talk about position over time, the rate of change is the velocity or the speed. If you don't care about direction. So like, you know, what's my rate of change if I'm driving here, right? Like 70 miles per hour or, at certain points. Um, but then what's my acceleration? Well, that's the rate of change of the rate of change. And so if you think of, you know, arithmetic sequences have constant velocity, right? They're just moving forward at the same rate. Uh, Quadratic sequences have constant acceleration, not constant velocity, but constant acceleration. That's this. So if you get to calculus, if you're taking calculus in the future or you already took it, then hopefully, um, I mean, I know you'll go into more depth, but if not, then it's just a fun little fact here. Okay, so one thing that is very useful in terms of sequences is computing, uh, or is trying to find the closed form. So for arithmetic, it's fairly straightforward once you know the common difference. Here, just knowing the second difference isn't really enough to like give you a formula. Like by formula, I mean we need to know what these capital A, B, and C are. Um, but how do we find that out? So the method I would say is straightforward, but it's not uh, necessarily easy, right? It's Let's see how we can do it though. So I'm gonna kind of rewrite some things here. So AN is capital AN squared plus BN plus C. And we want to find, so the goal is find A, B, and C, i.e. a closed form formula. The book uses a little bit different terminology, but it means the same thing. Okay, so let's kind of line these up. So A0, A1, A2, A3, A4. So, sequence, and it was 1, 2, 9, 22, 41. Okay. So what we can do is just start plugging in values into this formula, right? So when n is equal to 0, what do I get? Well, A0 is just 1 by this. I just know that it's 1. I know that the first term in the sequence is 1. But if I use the formula to try and with these coefficients, right, I could plug in these values because I know this must be true, right? So if I plug in 0 here, I get this. And I also know that the A0 term is 1. So that's how I know that these are equal. Okay, so if I simplify this, this is just 1 equals C. All right, cool. So I already found 1 out of the 3 coefficients. All right, let's do the next one. So we can get another equation here by just plugging in the next value. So from just seeing the sequence, I know that A1 is equal to 2, right? But also from what I know about quadratic sequences that they must be of this form, then I can plug in a 2 into n and see what happens. Sorry, plug in a 1 into n and see what happens because this is n equals 1. So then I get 2 equals A plus B plus C, but I actually know that C is equal to 1. Right? I know that C is equal to 1, so I can just use that there. And so A plus B is equal to 1. Okay, so it doesn't help me get A or B immediately, because I have two unknowns still. So there are infinitely many possibilities for A and B right now, just with this equation. But if I just try the next one in the sequence, so n equals 2, then, right, A sub 2, I know that A sub 2 is 9, because I know the first 5 terms of the sequence. And um, and then I also know that since it's of this form, I can plug in 2 and hopefully get something. 2 squared plus b times 2 plus c. Okay, so 9 equals, that's 4a plus 2b, and I still know that c is equal to 1, but helps. And then subtract 1 from both sides, 8 equals 4a plus 2b. And then divide, I can simplify this a bit, divide both sides by 2, you get 4 equals 2a plus b. All right, and then that's another equation. So it's still, that equation alone doesn't get me a or b, so it doesn't determine a coefficient. But now I have two equations with two of the same unknown, a and b, so I can set up a system of equations and solve that system. Right, so this is back to algebra. So it might be review, but we're going to go through it nonetheless because it might have been a while for some of you. Okay, so let's look at these equations. So 2a plus b equals 4, and a plus b equals 1. I lined them up this way. They're still the same equations, but I lined them up this way because, you know, there are many methods to solving a system of equations, and one is to just kind of cancel variables by subtracting one equation from another. So if I just subtract the first equation, sorry, the second equation from the first, or, you know, the way they're lined up now, then 2a minus a is just a single a, b minus b is 0, and 4 minus 1 is 3. So a equals 3. Nice. And then now that I have one of the variables out of a and b, I can get the other one just by plugging it into either equation. So if I just plug this into a plus b equals 1, then I get 3 plus b equals 1. And so I get that b equals -2. Okay. So there we go. That's all three coefficients. So the general form of a quadratic sequence is an squared plus bn plus c. But for this specific sequence, I know that the nth term is equal to 3n squared, because we found that a is equal to 3, minus 2n, because we found that b is equal to -2, plus 1, because we found that c is equal to 1. So we found a closed form of the sequence, which is great. Let's just check our result, see, get some evidence to see that it's good. What is a term that we know in the sequence? Well, we know A4. A4 is 41. So let's plug this in and make sure we get 41. So 3 times 4 squared minus 2 times 4 plus 1. So that's 3 times 16 minus 8 plus 1. 3 times 16 is 48 minus 8 plus 1. That's 40 plus 1. That is 41. Hooray. Nice. And, you know, besides just the practice of finding closed forms, closed form formulas, they're useful in practice, because if you have a formula, then you could compute any term you want without having to compute all of the previous terms. So if I wanted to know the 100th term and I didn't have this, then I would have to, you know, add add 6 to the common difference, or the second difference to get, okay, this one's and then going to be 25, and then I have to add 25 to that to get 66, and then I have to do that all the way up until uh, until I get to the 100th term. Or, and a computer could do that easily, but what if I had a sequencer or some function that, I needed to know the billionth term, or the trillionth term, or I wanted to know even if there was a closed form or something like that. So if I have a closed form, then I can, uh, then, you know, I can get any term I want without having to compute all of the previous ones, uh, which turns out to be pretty useful in applications. Okay.